In the last video, we got as far as figuring out that the area of this Koch snowflake, this thing that has an infinite perimeter, can be expressed as this infinite sum right over here. And so our job in this video is to try to simplify this and hopefully get a finite value. So let's do our best to actually simplify this thing right over here. So the easiest part of this thing to simplify is this right over here. So let's just focus on that. And then if we can get a value for this part that I'm bracketing off, then we can just place that value here and then simplify the rest of it. So what I've just bracketed off can be rewritten as 3 times 4 ninths, 3 times 4 ninths plus 4 ninths squared, 4 ninths squared, plus 4 ninths to the third power, third power, and you can go on and on and on. Plus 4 ninths to every other power, all the way through infinity. And lucky for us, there is a way to figure out this infinite, what is called a geometric series. There's a way to figure this out. And we do videos, actually I think I've done several videos where we prove the general thing. But I'll just do it by hand this time, just so that we don't have to resort to some magical formulas. So let's say that we define some sum. Let's say that we say this sum right over here. Let's call that S. So I'm going to say that S is equal to what we have in parentheses right over here. It's going to be equal to 4 ninths plus 4 ninths squared plus 4 ninths to the third power, 4 ninths to the third power, all the way to infinity. Now let's also say that let's multiply s times 4 ninths. So let me write that down here. So if we multiply s times 4 ninths, let me give myself some space here. So what's 4 ninths s going to look like? So 4 ninths s. So then I'm just essentially multiplying every term here times 4 ninths. So if I take this first term and multiply it times 4 ninths, what am I going to get? Well, I'm going to get 4 ninths squared. 4 ninths squared. If I take the second term and multiply it times 4 ninths, I'm going to get 4 ninths to the third power. And we're going to go all the way to infinity. So this is interesting. When I multiply 4 ninths times s, I get all of the terms here except for this first 4 ninths. And now this is kind of the magic of how we can actually find the sum of an infinite geometric series, is we can subtract this term right over here. We can subtract this pink line from this green line. So if we do that, clearly this is equal to that and that is equal to that. So if we subtract this from that, it's equivalent to subtracting the pink from the green. So we get s minus 4 ninths, s minus 4 ninths s, minus 4, let me do that in that pink color just so we know what we're doing, minus 4 ninths s is equal to, well, every other term, this guy minus this guy is going to cancel out. This guy minus this guy is going to cancel out. And that's going to happen all the way to infinity. And on the right-hand side, you're only going to be left with this 4 ninths right over here. Only going to be left with this 4 ninths. And then this 4 ninths, we can, s is the same thing as 9 over 9. So we could write this as 9 over 9s minus 4 ninths s is equal to 4 ninths. And so 9 over 9 minus 4 over 9 of something gives us 5 over 9. So this becomes 5 ninths s is equal to 4 ninths. And then to solve for s, and this is kind of magical, but it's actually quite logical, multiply both sides times the inverse of this, so times 9/5, so that we can isolate the s, times 9/5. These guys cancel out, and we get s is equal to 4/5. S is equal to 4/5. That's really, this is kind of neat. This whole thing right over here, we have just shown to ourselves is equal to 4/5. Is equal to 4/5. So this entire bracket that we did right over here is equal to 3 times 4/5. So this entire bracket right over here is equal to 3 times 4/5, or it's equal to 12. It's equal to 12 over 5, that entire bracket. So now let's go to our original expression, just so we don't lose track of what we're doing. We have the square root of 3, s squared over 16. And then we have this 4 here, 4 plus this whole thing right over here simplified to 12/5, plus 12 12/5. Now, just to add these two things, we can rewrite 4 as 20/5. We can rewrite this as 20. We can rewrite this as 20 over 5. And then 20 over 5 plus 12 over 5 is 32 over 5. So let me write this down right over here. So this whole thing right over here is going to be 32. 32 over 5. And this is really the home stretch now. This is very exciting. We're about to find the finite area of something that has an infinite perimeter. So it's going to be, let me rewrite it. I don't want to get messy in all of the excitement here. Square root of 3 s squared over 16 times 32 over 5. Times 32 over 5. And 32, we can divide both the numerator and the denominator by 16. 32 divided by 16 is 2. 16 divided by 16 is 1. And we are left with, and this is where we really do need a drum roll, the area of a Koch snowflake, where the initial equilateral triangle that we started with has each of its sides is length s, and they're all length s because it's an equilateral triangle, is, I'll do this in magenta, square root was going to be 2 times the square root of 3, 2 times the square root of 3, s squared, so whatever that side length was, all of that over, let's see, we use the 2, we use the square root of 3, we use the s squared, all of that over 5. So for example, if that first equilateral triangle, we started out with had a side length of 1, then the area of this crazy thing that has an infinite perimeter would just be 2 square roots of 3 times 1 squared over 5, or 2 square roots of 3 over 5. Anyway, I think that's kind of cool.